Hi everyone, I'm Jun. I'm a PhD student in computer science. My research interests focus on machine learning and data mining. In this semester, I'm the teaching assistant for the class of Intelligent Systems. It is my first lecture. Today, I will cover the topic about the genetic algorithm. The name seems really complicated, right? I will try my best to introduce this topic as simple as possible. So let's get started. At first, I will introduce some concept about this algorithm. Genetic algorithm is a heuristic search algorithm inspired by Darwin's theory of natural evolution. So what's the heuristic? Heuristic means that we want to find out a more quickly or approximate solution when classical methods are too slow or even failed. For example, in the first day of class, we want to find the classroom. Of course, you can search the room and use some broom method to search the room building by building. It may cost you the whole day to visit the campus. Actually, we will search the building based on the course we take. For example, we will go to the science building at first if we take the computer science course, and then we will have a look at the map at the entrance of each floor and check if the ID of the class is matched. If matched, we will go directly inside this floor and continue search the room. Otherwise, we will go to other floor to check the map again until we find the ID. So similarly, genetic algorithms imitate the progress of natural evolution. For example, organisms such as animals produce a number of offspring which are almost like themselves. Variation may be caused by the mutation or sexual reproduction. Some of these offspring may survive to produce offspring again. So next, we will discuss some concept about this algorithm. Genes are the base element to build an organism. A sequence of genes forms a chromosome. So here we denote that each individual only carry one chromosome. So one individual means one solution. This individual may be the optimal solution for us. A population consists of a set of chromosomes. So this figure represents the relationship between the genes, chromosome, and population. You can see genes is only one element, and chromosome is a string of genes, and several chromosomes consist of this population. So next we will talk about what's the initialization. At the beginning of the algorithm, we will initialize the population just by randomly generating some individuals. So this initialization allows the entire range of possible solutions in search space. So the next concept is the finish function. This function measures the quality of solution. We can say this finish function is the objective function. So the termination is a stop criteria. We need to decide the termination for every problem. The algorithm terminates if the stop criteria is reached. In other words, produced offspring doesn't significantly change. This could be one termination. Of course, we can use another termination for another problem. It depends. So next, I will introduce three basic genetic operators. The first one is the selection. Individuals with high finish score have more chance to be selected for reproduction. Yeah, it's very easy to understand. Individual with high finish score means that it is close to the optimal solution. So we will go towards this direction. The second operator is the crossover. A crossover point is randomly chosen. Offspring are created by the exchanging the genes of parents among themselves until the crossover point is reached. So from the left-hand side of the figure, you can see the red line represent the crossover point, and there are two individual A1 and A2. So the element inside this individual is genes. So you can see two individuals, they are exchanging the genes until they meet the crossover point. And the further operator is the mutation. Some genes can be mutated with a low random probability. So you can see the right-hand side of the figures. And the upper row is the before mutation, after row is the after mutation. You can see between these two individuals, some of the genes are just randomly shift from 1 to 0 or 0 to 1. So in the next, we will introduce the simple genetic algorithm. It's just a pseudocode. So you can see at the beginning, it initializes the population randomly, and then it computes the fitness score. After that, you go into the while loop. Inside the while loop, you will do 3 operations: selection, crossover, and mutation. After that, it will update the fitness score. And inside this while loop, there are line 5 to 8. We will repeat this progress until the stop criteria is reached. It is a simple version of the genetic algorithm. So in the next section, I find 2 simple examples from the internet to help people to better understand this algorithm. So here is the example 1. Given a set of data points x and y, we want to fit the polynomial function. For example, we could use least squares regression to fit this function. It's a common method we can use. Most specifically, we compute the mean square error for all data points and pick the lowest sum and the best fit. Here you can see the function about the mean square error. So we assume that we don't know this great method to solve this simple question. So right now we want to use the genetic algorithm to approximate the best solution. So this example can help us to better understand how to compute the fitness score. So our formula is y is equal to ax squared plus bx plus c. So the gene here, we denote the genes are A, B, and C. And the chromosome is the array of A, B, C. Know that the array A, B, C is the solution we want to find, because we want to find the best coefficient and to fit this function. So for every data point x, y, right, know that I use the red color to highlight the actual data point. So for every actual data point, we compute the predicted value y bar, and then we find the mean square error over all actual data point. For example, for individual 2, 3, 5, and 2 data points, so when x is equal to 1, the y bar is equal to 10. When x is equal to 2, the y bar is equal to 19. So we got this 2 predicted value, and then we can compute the mean square error between the predicted value and the actual value. So we got the mean square error is equal to 6.5. For these 2 points, the fitness score of this individual is 6.5. It's very easy, right? So Next, we will talk about another example. Example 2. Given a set of x within the range between 0 and 31 inclusively. So we want to find out the maximum value of function y within this range where y is equal to x squared. Note that the x is integer. Here we define the individual as any integer x within this range, and then we encode the integer from decimal to binary. So here, why we want to encode the integer? Because our goal is want to find out the value x, make the function y has the maximum value. So the optimal solution is one integer. So we just encode this integer into a chromosome so that we can do it as following steps. The first step is initialization. So for the initialization steps, we assume that the size of population is 4. 4 is given by us. We can assign 6 or 8, but for this simple question, we only need 4. So the population includes 4 individuals. And we use 5-bit binary to encode the chromosome. Why we use 5-bit binary? Because the search space is from 0 to 31. So we can use 5-bit binary to represent the maximum number 31. So 5 bits is enough for us to represent the whole search space. So here we use 5 bits, and know that each individual has only one chromosome. So we randomly pick 4 individual, means we randomly select 4 number within this search space. The 4 number at the beginning is 13, 24, 8, and 19. So we encode this 4 number into the binary. You can see the binary is following by the number. For example, for the first individual, the number is 13, so its binary is 01101. In the next step, we compute the fitness score. We define the fitness function as the fx is equal to x squared, and then we compute the fitness score for each individual as following. For example, for the first individual, is 13 times 13 is equal to 169. So we compute 4 fitness score by this method. In next step is execute the genetic operations. First, we will use the selection operators. We compute the probability for each individual by this formula. So the total sum of the fitness score is 169 plus 576 plus 64 plus 361 is equal to 1,170. So 169 over 1,170 is equal to 0.14. So we got a probability of these 4 individuals. And then we compute the cumulative probability for each individuals. So we got this 4 accumulative probability. Know that the total sum of accumulative probability is 1. So the last number must be 1. And then we generate 4 random numbers from this the range of 1, from 1 and to the 0. Oh, sorry, it's from the range is from 0 to 1. Sorry. And so we got the 4 number. So know that the individual with higher fitness score, so it has higher probability to get more offspring. So here you can see for the individual 2, it has the highest fitness score, 576. So here he got 2 offspring, and the individual 1 and 4, they got one offspring respectively. And so you can see right now you can see right now the X1 and X3, they all are 24. They all come from the original individual 2. So in the next operation is the crossover. So we assume the crossover rate is 100%. It means all individuals get involved this crossover. So we assign X1 and X2 for the first pair and X3 and X4 for the second pair. So we exchange the last 2 genes for each pair. So we highlight the last 2 genes for each individual. You can see from the X1, for example, the last 2 bit is 0, 0, so it's exchanged to the X2. So right now the new X2 is 0, 1, 1, 0, 0. So the number is changed from 13 to 12. So next operation is the mutation. We assume the mutation rate is 0.001. So right now we have 4 chromosomes. Each chromosome has 5 genes. So totally we have 20 genes. We set the mutation rate is 0.001. So only 0.02 genes will mutate in this round. Since 0.02 is smaller than 1, so the mutation is not happening in this round. So the individuals for the second generation, it remains the same. Note that both the crossover and mutation will increase the randomness. However, the individual exposed to the mutation will have exponential increase in search space. How to understand this works? Let's say crossover only change the last 2 bits of the individuals. It may have a very small change for the number. However, the mutation, it may randomly change any bit of the individual, and this mutation may be expressed very quickly. So we say that it has exponential increase for the computational cost. Next, we will, after these 3 operations, we will update the fitness score, and let's say we just use the fx is equal to x squared. We use this formula to recompute the fitness score, so we can get this 4 number. So inside this while loop, we repeat the step 3 and 4 until the maximum individual doesn't change. Here we define the stop criteria is equal to the maximum individual doesn't change. So, but for other problems, you can definitely define different stop criteria. It's very flexible. So from this figure, we can see in the first round, we randomly generate 4 individuals, and then in upcoming round, you can see the number is approaching to the optimal solution. By the end, the number had reached the optimal solution. So it's the 31. So the maximum value is 31 times 31 is equal to 961. So in next section, we will make a conclusion about this algorithm. So in previous section, we use 2 simple examples to help people better understand this algorithm. In brief, this algorithm is a heuristic search algorithm. It is better than the brute force method. We can try it when we have no suitable approach. For example, we have no better method to solve this problem, and we don't want to use the brute force method, so we can try this genetic algorithm. So this algorithm is easy to be executed by parallel computing. It's easy to understand. For example, in previous example, we can assign individual 1 and 2 to the first machine, and we assign individual 3 and 4 to another machine, so that we can compute these two pairs in different machines. So the third advantage is the biggest advantage is that the fitness function is not necessary to be continuous and differentiable. It's very important. For example, for the neural network, when we compute the gradient must be the differentiable. Otherwise, we cannot propagate the gradient, right? And for the disadvantage of this algorithm, the first is do not scale well with complexity. Again, for example, for the mutation operation, the individual exposed to the mutation will have exponential increase. So it means that if the mutation rate is higher, the mutation is it will be affect more and more individual. So it's difficult to scale well with this complexity and others. We have talked about the stop criteria. It may be not clear in every problem. So for the easy problem is we can very easily find the stop criteria, but it's not easy to find stop criteria in every problem. And the last one, the last but not the least, the exploration may be trapped in the local optima. So I borrow a figure from the internet to help you better understand what's that. So in this figure, you can see the only one global minimum is the G point, and the rest A, B, C, D point is the local minima. And for example, for this genetic algorithm, if the stop criteria, for example, it is reached to the B point, the local minimum, and the stop criteria is reached, so the algorithm will jump out the while loop. So it's finished, but actually it didn't go to the global minimum. That's all. So here I left some links for you, and if you are interested, you can search this tutorial to have more exploration about this algorithm. It's funny. Thank you.